This lab deals with fundamental physics principles such as Faraday's law, including magnetic flux, EMF, induced current, F equals ma, and the Biot-Savart law. In this lab, I will collect observational data of a magnet falling through a conductive tube of aluminum foil. And I'll model the magnet/tube interaction computationally, and I'll compare my computational predictions with the observed data. So the experiment materials needed were my phone, the aluminum foil tube, a magnet, and a ruler. So the procedure: drop the north end of the magnet through the aluminum tube. I made sure to film this. So after the magnet fell through the tube, I went through the videos and I saw how long it took the magnet to fall, and I repeated this 5 more times. So the results of my experiment: here are the measurements of my aluminum tube. I did 6 trials, and the average amount of time for the magnet to go through the tube was 0.85 seconds. So the purpose of the code is to simulate a bar magnet being dropped through a conductive tube. The bar magnet is modeled as a point dipole, and the conductive tube is modeled as a stack of non-interacting conductive rings. So here is my code. Here's it running. And the result was 0.93 seconds. And here's the code itself. So right here, they created the aluminum foil. I put in my values that I measured. Here I created the bar magnet. I put in the mass and the mu mag from lab 3. Here I created a function to calculate the magnetic field of the bar magnet. Step 3, I created a function to calculate the magnetic flux. And then I edited the other lines that it needed. And I got the result I just showed. So the result of the code: it took 0.93 seconds for the magnet to fall through the simulated aluminum tube. So questions. The intensity of the coloring on the tube indicates the magnitude of current flowing through each ring. Red and blue indicate current flowing in opposite directions. Which color corresponds to clockwise current as viewed from above, and which counterclockwise? How do you know? So blue is counterclockwise, and I know this because of the right-hand rule. If I point my thumb facing downwards in the direction that the magnetic field from the bar magnet is, the current is clockwise. I know now that I need to make it opposite to that due to Faraday's law. So the blue appears first, so it's counterclockwise, and because red is in the opposite direction, it would be clockwise. So what happens to the dynamics of the system when you flip the magnet around? The induced current would start out as clockwise at first, then using the right-hand rule, Faraday's law. How does the total time in tube of your real-world system compare to that of the computational model? So the total time in tube that I recorded experimentally was a bit less as compared to my computer model, and I believe this is due to human error in me measuring the aluminum tube. So what does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? So initially the bar magnet accelerates downwards due to the force of gravity, as you can see here. But at the bottom of the first dip in the graph, the magnet starts to experience the force created by the aluminum tube against the magnet. That's right here. And then the bar magnet slows down as the force created by the aluminum bar's induced current is held constant against the magnet, and this slows its descent. But as it gets out of the tube, it continues its accelerated descent. So what if the resistivity of the conductor reduced as close to zero, as close to zero as possible? So R equals V over I. So a smart R value means that I has to be very large, and a large I means that the force against the magnet is even larger. This would mean that the magnet would end up going even slower while flowing through the tube. And what if holes or slots were cut into the tube? How would this affect the ring currents in your model? It would result in less force against the magnet as there is less I or current created. And you can see this in the picture below. There's not as much current, so not as much force against the magnet falling through. So conclusion. While the magnet falls through an aluminum tube, it induces a current in it. This induced current results in a force against the magnet which slows its descent through the tube. The experimental model and the computer model differ slightly, but most likely due to human error in measuring the dimensions of the aluminum tube.